Hello all, welcome back to Calculus. We are entering chapter 4, which is applications of derivatives. Of course, you've just finished your favorite application of derivative, the related rate, but don't worry, it does get better. We are going to start chapter 4 with an actual easier application of derivatives, which is starting to look at pretty much what the derivative tells us about a function. In pre-calc, you learn how to find end behavior, you learn how to find where it crosses the x and y axis. Now in calculus, we're going to be able to tell a little bit more by looking at the first and second derivatives. It's going to tell us about the shape of the graph, where it has mins, where it has maxes, how the graph curves, if you will. We are going to start that by looking at another value theorem called the extreme value theorem, which is obviously going to talk about mins and maxes. So when we talk about extrema or extrema, if you're fancy, in pre-calc, we have no choice because we don't have a derivative yet than to talk about a maximum point as it relates to all of the other points. So they define a maximum as a point where all the other points are lower, which is a fine definition, but really difficult to find that point based on that definition. Same thing with a minimum. They describe it as a point where all the other points are higher. They're like, this point here is lower than all the other points. True, but not necessarily helpful if I'm trying to find it. Luckily, calculus comes along and it gives us a much better way to find it. Okay, the extreme value theorem tells us something pretty important about a function. And I want you to notice that it starts the same way that the intermediate value theorem started. Remember, intermediate meant between, and it started with, it had to be continuous on a closed interval. And that same statement is here when you are using the extreme value theorem. If you plan to state it, you have to say, since the function is continuous on a closed interval, exactly the way you did with the intermediate value theorem. So we're going to say, since the function is continuous on a closed interval, the extreme value theorem states that, and this is what it tells us. There has to be a minimum and a maximum on the interval. It seems like a silly statement, but those two criteria have to be there in order for there to be an absolute low point and an absolute high point. So for example, look at this graph. Simple graph, y equals x squared. If you look at the interval from 0 to 4, including 0, including 4, obviously you have a low point at 0 and you have a high point at 416. Right? Easy peasy. But look what happens if I open up that interval. In other words, if instead of this point at 0 being a closed point, what if I open this point? Okay. Now, I still have this maximum point, like clearly 416 is the highest point on the interval. Fine. But when I come over here to the lowest point, it doesn't matter what point you name. I can name a point that's closer to this point right here, 0, 0. But we'll never actually get there, right? Because we know that this open point means you may approach this point. You may get infinitely close to that point, but you can't ever go there. And no matter what point you name, somebody else can come along and name a point that's lower. So for this, because this point isn't included, we have to say that there is no minimum on this interval. And this is what we mean when we say it has to be continuous on a closed interval. Extreme value theorem is going to guarantee that minimum and that maximum as long as it's a closed interval and as long as we're continuous. Okay. Look what happens here on 0 to 4. If I leave the 4 out, now this is colored in. Cool, I have my minimum at 0, 0. But now I'm missing my maximum because if this point is open, I can't approach it. I can only approach it. So I have to say no to a maximum on that particular interval. Now, what I want you to notice here is in this first three examples, 0 and 4 are the endpoints, and they also happen to be the mins and the maxes that we're talking about. So look at these next few. We're talking about a new interval here. We're going from -1 to +2. So from -1, is that included? Yep, to +2, included. I clearly have a maximum here at 2, right? So my maximum is at 2. And my minimum is right there, right? That's my low point. It's at 0, 0. And what I want you to notice here is even when these intervals change as far as including or not including endpoints, I cannot include this 1, this -1, and it doesn't change anything, right? If this -1 isn't included, it doesn't matter. I still have a minimum at 0, 0. I still have a maximum at 2, 4. If this 2 fails to be included as well, I still have my minimum. I just lost my maximum. And again, the point is this, the same thing with intermediate value theorem. This is an if statement. It's not an if and only if statement. So they're saying if it's continuous on a closed interval, then I promise you're going to have a minimum, you're going to have a maximum. If that statement fails, like it does here and here and here and here, maybe I'll have a minimum and max, maybe I won't. No promises. But you cannot ever say, this function isn't on a closed interval, so there won't be a min or a max. You don't know that. If it's continuous on a closed interval, yes, you have a min and a max. If either of those criteria fail, it's a maybe. Okay, so let me show you a big fat example of that. I stole this picture from a book a couple years ago. It has basically every way you could have a min or a max or something funky going on. All right, so notice this graph here. You have an absolute minimum right here at A. But then as you go through this function, you also have these local mins. Some people call them relative mins. So depending on the book that you read, you might see local, you might see relative. So on this interval, this is the absolute lowest point, right? But you also have these points here that are low points relative to the points around them. Same thing here. You have an absolute max right here, but you also have a local max here. Okay. Now, what we're going to be looking at to find mins and maxes is we're going to be looking at derivatives, right? And we know that anywhere where the derivative is 0 is going to potentially be a peak, right? A peak or a valley. And what this graph shows very nicely is the danger of that. Because notice here and here, you get a 0 derivative, but that's not a min or a max. The other thing this graph shows is the other danger. That point right there is definitely a maximum, but the derivative isn't 0 there. So one of the things that people like to think, and because we're pretty good at understanding the derivative being slope, is that if I want to find the mins and maxes, all I have to do is go look and see where the derivative is equal to 0. That's easy, right? Those are my horizontal tangents. That's where my mins and maxes are. End of story. Not end of story. Okay. It's possible to have a 0 tangent and not have a min or a max, like these 2 points. It's possible to have a min or a max where there is no 0 tangent. Okay, so how are we going to find them? Because we have to be able to find them. All right, look at me with my dots. Here we go. I'm going to talk about how to find them today. The next time we see each other, we'll practice finding them together. If you are looking for mins and maxes, there's really only 2 places you need to look. Okay. The first place you need to look are the endpoints. And I say that's the first place you need to look because it's always the place everybody forgets to look. If they give you a closed interval, the first place you look for mins and maxes are the endpoints. So I make what's called a candidates table. And in that candidates table, I put down all the X values that are potential mins and maxes, places I need to look. Candidates, if you will, for mins and maxes. It's often like a presidential primary, lots of candidates. Okay, so first place we're going to look. So if you've got 2 included endpoints, right there, you have 2 candidates. If you have no included endpoints, no candidates. And obviously you can have one or the other. All right. The other place we look is that derivative, and we are looking for what are generally called critical points. So you're looking for endpoints and critical points. There's 2 ways a point can turn out to be critical. The first way to be critical is that is a point where the derivative equals 0, and that's the obvious one, right? If the derivative is equal to 0, you've got a horizontal tangent line, which means it's either a maximum point or a minimum point. The function is either peaking or bottoming out. It's got to be one of those two. But the other place, the other critical point, is place where your derivative fails to exist. We're talking about corners, cusps, vertical tangents, discontinuities. Now remember, if there's going to be mins and maxes, if we're going to be applying the extreme value theorem, then it better be continuous on the closed interval. So if there's a discontinuity, we already kind of have our eye on this thing. But places like corners and cusps are tricky because the function is still continuous there. Think about everybody's best friend, the absolute value graph. Obviously, this graph has a minimum right here at 0, 0. But that's not a 0 derivative. That is a place where the derivative fails to exist. That's a corner. So what we would see if we were looking at just the derivative of that function, remember, is a piecewise function. If I wanted to write f of x, the absolute value of x, as a piecewise function, which I know you love to do, I would say, well, that function is x as long as x is greater than or equal to 0, but that function is negative x if x is less than 0. We'll take the derivative of that, and you get 1 and negative 1. We learned, before you ever knew what a derivative is, that this is a big fat no-no. If the slope from the left is negative 1, and the slope from the right is positive 1, we've got a problem, right? The limit fails to exist. I do not have a derivative there. That's that kind of critical point. That's this guy. So as we're looking for minimums and maximums of functions over the next few days, we're going to take that derivative and we're going to do two things to it. We're going to say, where does it equal 0 and where does it fail to exist? So all the times that you've said to me, do I have to simplify this? Do I have to simplify this? And I say, nope. You only simplify if you have a reason to simplify. This is going to be your reason to simplify. Because if you do a quotient rule derivative and you have this big nasty derivative, right? Big nasty numerator. I need to know when that thing is equal to 0. You're going to want to simplify that numerator to find out. If I need to know where that function fails to exist, you're going to need to simplify that denominator to find out. Because I need to know when that denominator is going to go to 0. So there is going to be some simplification here. We simplify if we have a reason to simplify. This is one of the reasons. Okay, so like I said, we will practice this in class. For now, I just wanted to give you the theory of it. Enjoy the rest of your day, and I will see you soon.